Multi-threading issues such as what is condition variable, how to design a system that can handle 500 million users. Questions like this are not only critical for job interviews, but also very important for our daily work. In this video, I will tell you 5 stories that can help you to master multi-threading programming. This story helped me tremendously before. So nowadays, if you give me any multi-threading questions, within 5 seconds, I will get it and find a solution for it. It is that powerful because these stories actually tell 5 design patterns that are critical for multi-threading programming. In this video, I will not only explain what these 5 patterns are, but also share the source code to you so that you don't have to start from scratch. So these 5 design patterns, they build upon each other. They start from the very basic, but in the end, they will cover the most sophisticated scenarios. So let's waste no time and dive into our stories. So the first story is called Blackboard Fighting. It's explaining what issues you can have in multi-threading programming and also introduce a design pattern called safe and smart lock, which will help you to resolve those issues. So you have a blackboard and you have 2 gentlemen, Danny and Peter. Both gentlemen want to write their name on the blackboard. Danny wants to write, "My name is Danny," and Peter wants to write, "My name is Peter." The problem is these 2 gentlemen don't cooperate each other. So when Danny is writing my name, and before he can continue, and Peter jump in and write my name is Peter again, and then Danny has a chance to finish his words. So in the end, because these 2 gentlemen don't cooperate each other, the blackboard will end up with something like this. My name is Danny Peter. This kind of lack of collaboration between 2 people is precisely what happened in a multi-threading environment. The blackboard, in programming term, we call it shared resource because it is shared by both Danny and Peter. And Danny and Peter, they represent 2 threads, Danny's thread and Peter's thread. And the fact that they both simultaneously try to write down their name end up with rubbish output, we call this race condition. Let's use a code to illustrate this. So we create a C++ file called thread-samples.cpp, within which we include all the necessary headers, thread and IOStream. Later on, we will use Q, so we include this up front. And of course, we declare the namespace std. The first thing we need to do is to write a function called DannyWrite. So this function takes 1 parameter, blackboard, which is a string reference. If you don't know what the reference is, basically in C++, a reference allows you to modify blackboard, which is defined outside of DannyWrite. And what this function does is try to add my name is Danny into the blackboard. So, but between each words, we will insert a sleep function to force DannyWrite to sleep from 1 to 3 milliseconds to slow down the writing process, because we want later on Peter has a chance to jump in before Danny finishes writing. If Danny writes too fast, Peter might not have the chance to jump in before Danny finishes writing, and then we cannot demonstrate the issue. We define a Peter write exactly the same, except that it writes my name is Peter instead of Danny. So these are the 2 functions. And then we will define a test function we called demo resource conflict. Within this function, we will of course define our blackboard, which is a string. And then we will create our first thread, we call it Danny's thread, and pass in Danny function and the parameter blackboard into this thread. For those who don't know how to create a thread in C++, here's a quick explanation. So here, Danny's thread is a thread object. It takes 2 parameters. The first one is a function name, which is DannyWrite we defined here. And the second one is the parameter for the Danny's write function. So because here it accepts Blackboard, so here we pass the Blackboard, which we define here as a second parameter. And we put this into a reference wrapper. For those who don't know what reference wrapper is, you can Google it. Basically, this wrapper allows you to pass the Blackboard object as a reference. That's all you need to know. After we create Danny thread, it will immediately be executed in computer. So bear that in mind. And next, we will create a second thread we call Peter thread, which do exactly the same thing, but to call Peter write. And then we will wait the Danny thread to finish, and we will wait the Peter thread to finish. How we wait? We call the join function. And after both threads finished, we will output what the two threads wrote on the Blackboard. So we'll put the stuff to see out, and let's see what happened. And of course, we need to put this function demo resource conflict into our main function so that we can see the result. So now we finish the code. Let's compile it and to see the result. So it compiled, and let's run it and to see what happened. You see here, the output is my name is Danny Peter, so it's rubbish. And the reason, let's explain that again, is because when these two threads running simultaneously, both threads were trying to write to the Blackboard string because they did not collaborate. So when Danny's write function was trying to write its string, and before it can finish, Peter write thread jumps in. That is what you see. How to resolve this problem? It's very easy. See, in the Danny Peter story, both gentlemen had their own pen so that they can write whenever they want. In next story, we will give these two gentlemen only one pen. So whoever can get the pen first has the right to write down his name. After he finishes, he will have to return that pen, and the next gentleman will get that pen and write his words. The key here is that we will have only one pen for two gentlemen, and at any given point of time, only one gentleman can have the pen and can finish his work. The second critical point is that after the gentleman finishes his work, he must return that pen. Otherwise, the second gentleman will wait forever to get a pen. So that's also very important. So let's use code to demonstrate this. So here we write a new function called Peter write with mutex. And this function takes an extra parameter, we call it mutex. This mutex is a pen in our story. At any point of time, only one gentleman, either Danny or Peter, will get a pen. In our case, we get the mutex. But how exactly does Peter to get the pen? In this case, mutex is actually, it calls a mutex lock function. The lock means it gets a pen. And then we call the previous function Peter write so that Peter can write its name on the Blackboard without interruption because he gets a pen. Danny doesn't have the pen. But after Peter finished its work, it's very important for Peter to return the pen. How does he return the pen? Unlock it. Unlock the mutex. So this is the new function, Peter write with mutex. And we need the Danny version of the new function. Everything is the same. Danny locks the mutex, Danny write, and then Danny return the pen, unlocks the mutex. So here's our test code. As usual, we define the Blackboard, and then we define the new variable mutex. This is our pen, very important. And then we pass a new function, Danny write with mutex to the Danny thread. And also we pass a new parameter mutex. So we do the same thing for Peter thread. And then we let them do their work. We wait for both threads to finish. And then we print out what is on the Blackboard. Of course, we need to put the test function into our main function. So let's run the code and to see what happens. So we compile it and we run the code. So now everything works properly. My name is Danny and my name is Peter. Beautiful. However, this version of code has at least 3 potential problems. So the first issue, what if any of these 2 gentlemen forget to return the pen, in our case, to unlock the mutex after they get the pen, after they lock the mutex? There are several scenarios that this can happen. The programmer just forget to call the unlock function, and there's an exception happening during the thread execution. Let's see, when Peter called mutex locks, and when the thread is trying to write stuff onto Blackboard, and boom, for some reason there's an exception, and so the thread dies, and there's no chance for this thread to call unlock function. And in this case, Danny's thread will wait because the mutex will be locked forever. Fortunately, C++ provides a unique solution to resolve this issue. In its standard library, it provides a class called unique lock, which will guarantee that you unlock the mutex. How does it do it? Because C++ has a unique feature called destructor. This will be guaranteed to call once an object gets destroyed, either because of an exception or because it just finished its works and goes out of scope. Either way, if you put the unlock function into the destructor, it will be guaranteed to call. So what this means is that using unique lock, you only need to lock the mutex and you never need to unlock the mutex because the system will automatically unlock it no matter what happened, even if you encounter an exception. So this unique lock is the first part of our design pattern. It's a smart lock because it can automatically unlock it. That's why we call it smart lock. So let's look at the code, how we implement this. So here, instead of we write directly a mutex lock function, we delete that and we will replace it with this line of code. Here, we just created a lock object which will lock the mutex automatically. Because it's a smart lock, we don't need to unlock it. So let's delete this unlock function. So this is how we use a smart lock. We lock it and we let Peter to do its work. And after Peter finishes work, the function will finish and will go out of scope. So automatically, the mutex will be unlocked. And even better, so even if we are executing the Peter write function and there's an exception happened, the lock will guarantee the mutex be unlocked. Isn't that beautiful? So let's do the same thing to the Dennis write mutex function. Now let's compile the code and see what happened. Compile it and run. See, it works as before, just as if we lock the mutex directly. So now we understand the first part of the pattern, the smart lock, and we resolve the issue that if somebody either forget to unlock the mutex or an exception happened and we never get a chance to release a lock, we got this issue covered. But we still need to cover the last issue, which is what if somebody forget to lock the mutex in the first place and then they access the resource directly? In our story, what if Peter doesn't respect the rule? Instead of using the pen shared by Danny, he actually pull up his own pen, and while Danny is writing on the blackboard, he is using his pen writing his name on the blackboard. He completely bypassed the pen mechanism. And this could happen either because of a junior developer who is not familiar with this lock and unlock mechanism, or because your team is developing a very complex system and somebody somewhere forgot to lock the mutex and access the resource directly. Even in our case, what if that somebody, instead of calling the Peter write with mutex, it just make a human mistake. Instead of let the Peter thread calling the write function Peter write with mutex, we mistakenly call the Peter write function, which doesn't have the mutex protection. And if you put these two lines of code together, all those errors will come back. And how do we resolve this issue? This is the second part, the safe part of the design pattern. The concept of this solution is very simple. Instead of allowing Danny and Peter to write directly on the blackboard, we actually put the blackboard into a safe so that either Danny or Peter cannot write on the blackboard unless they got a proper lock to unlock the safe. That's it. Before they can write onto the blackboard, so they have to use the lock to unlock the safe so that they can get the access to the blackboard. So this part of the pattern, we call it the safe part of the pattern, resolves the issue. What if a developer forget to lock the mutex? So let's take a look how we implement this solution. So the implementation of this concept of safe in this design pattern is a class we called mutex safe. It's a template class. It's actually a combination of two key components, mutex and the resource it tries to protect. That's why it has two private data members, the mutex itself and the resource pointer it tries to protect. So for the resource, you have to pass the resource pointer in the constructor and delete the resource when the mutex safe is destroyed. This means that the mutex safe object owns this resource it tries to protect, which we will show it in our code later. And because the mutex safe class is a mutex, that's why it implements all three key APIs of mutex, lock, unlock, and try lock, so that it behaves exactly the same as a mutex object. And the key of this class is a function acquired. It does nothing more than just return the resource, but it accepts a parameter unique lock object. This means that this function forces you to pass it a lock object. This guarantees that you cannot access the resource before you lock the safe object. So now we understand how mutex safe works. Let's use it to protect our Blackboard. So because Blackboard is a string, let's type define a mutex safe string as a string new type. And then we write a new function to allow Danny to write his name safely on the Blackboard using our safe mechanism. So we write the function as safe Danny write, which takes a parameter as a safe instead of a string. So within this function, we will create a log, but this time instead of a log mutex, we log the safe itself. And then we acquire the Blackboard from the safe by passing the log we just created to the acquire function. So since we get the Blackboard, we call the Danny write function as we just did before, and then we return. And we do this to the Peter write. And after we finish these two functions, let's write a test function to show how we actually use it. So the function name is called test safe smart lock. Within this function, of course, we create the safe first. And when we create the safe, we new a string as our Blackboard. Remember what we said, a safe will own the resource it tries to protect. So in this case, safe owns the Blackboard, the string we just created. And now let's create the Danny thread. This time we pass the newly created function safe Danny write instead of the old function. And then we pass the safe instead of the Blackboard into this thread. We do the same to the Peter thread, and then let's wait them to finish, and then let's try to print out the Blackboard. But remember, because we put the Blackboard into the safe, we cannot access Blackboard directly anywhere. So this time we have to lock the safe again, and then we acquire the Blackboard in our main thread, and then we print it out. And then, of course, we put this test function into our main function. It looks very similar. Let's compile the code and let's run the code. And everything runs smoothly. So now let's compare this traditional mutex lock and unlock code with our safe code to see what's the difference. Let's put the code side by side. So if you compare these two versions of code, the mutex safe version and the normal lock version, the only two things you need to change. Number one, when you lock the safe instead of the mutex directly. And number two, before you can access the protected resource, you have to acquire it and pass the lock you just created to the acquire function. This guarantees that you cannot forget lock this resource. That's it, no other changes, but it helps you to avoid the human errors that is very difficult to debug later on. Okay, now we understand the safe and the smart lock design pattern. Let's move to the next story where Danny needs to keep watching the stock price changes because he wants to sell his stock at $90. However, nobody knows when the stock price will change, so Danny has to keep watching the stock change all the time. This leaves him no time to do his other work. By the end of the story, you will find that Danny finds a very good solution to solve this problem. You can watch the next story here or down below. This channel is all about digital transformation and technology. If you are interested in these topics, please join our community down below where you can discuss these topics with other people with the same interest.